Okay, yeah, I'm here to talk about our latest work, conformal prediction on the ambiguous crown tooth. And just to set the scene a bit, what the context of this work is that we're very, very interested in classification in safety critical applications, especially in health. And in these applications, we very often have various problems that we need to deal with that make uncertainty estimation particularly difficult. This includes that we usually have a quite rich structure on classes, where we have like hierarchical class distributions. We have complex interactions between classes, as indicated in the middle a bit. We also have rare classes. We have a long tail class distribution, as indicated on the left. And then finally, and this is what this work will mainly be about, is very often the true crown tooth might actually be unknown or to a large extent uncertain. And just to illustrate this on a couple of examples, I guess everyone came across a series of papers that basically showed that on many of the common benchmarks that we use, especially in computer vision, we actually have labeling errors, right? So on MNIST, for example, we all can have a look, and we can, of course, disagree whether this is a 5 or 3. It might be an ambiguous case, but in most of these cases, we can usually identify label errors because we, as ML researchers, are actually able to solve this visual recognition task to some extent. Now, in safety critical applications, this is usually not the case, right? So if we look at health data, for example, we as researchers, we can't label the data ourselves. We can't say, is this a labeling error or not? So what we can do is we can ask experts, right? Asking experts, of course, is expensive. Whenever we ask a doctor to label anything, we are taking time of the doctor away from the healthcare system. So some patient out there may not be able to see this doctor because the doctor is labeling for us. But on top, because these tasks are difficult, experts also tend to disagree, right? And this disagree might be a problem of the annotators, inexperienced annotators, bad labeling tool, and so on. It might also indicate that there is some underlying uncertainty that we are not capturing correctly. And this sums up kind of the context of today's talk. So just as an outline, I'll briefly skim over conformal prediction. I'm pretty sure that most of you kind of know the basics, so it will mostly be about notation. Anyway, if anything's unclear, interrupt me. And then I'll start talking about the main part of the paper called Monte Carlo conformal prediction. And I'll basically walk you through 3 questions. So I will spend actually a large part of the talk on the first questions, basically asking where our crown tooth comes from, that we usually use for calibration, but also for evaluation of conformal prediction. And then I'll basically walk you through, okay, if this crown tooth is uncertain due to some reason, for example, that annotators disagree, how can we handle this during conformal calibration? So this will be the main part. Okay, to dive right in, just for notation, I'll assume that we have a model pi here that somehow assumes the posterior distribution of our true labels y given the inputs x. So we are, again, considering a multi-class classification problem. And our goal is to predict these confidence sets C of classes. So we have capital K classes here. C of x is my confidence set. And I want to do this in a way that I have the so-called coverage guarantee that I guess everyone's familiar with, where I basically say that marginally across my test examples, the probability of the true label y being included in this confidence set is lower bound at 1 minus alpha. Of course, usually this is a tight bound, but I think for simplicity, we'll just consider a lower bound. And as you all know, the power or the advantage of conformal prediction here is that this alpha is user specified, right? So you can give me any alpha you want, and I can construct the confidence sets accordingly. Because we have this coverage guarantee, the variable metric that we usually evaluate is inefficiency, so the average confidence set size. And then the advantages of conformal prediction are that it's very lightweight on assumptions, so we just require exchangeable calibration examples. It's independent of the model and the distribution. And just to note, and I'm pretty sure you're all aware, but it will get important later, the coverage is, of course, marginal over examples and implicitly also over the calibration set. So it's simple conformal predictor that I'll use throughout the talk is just a simple split conformal predictor, where at test time we construct the confidence sets by thresholding these conformity scores that I'll denote E, right? So EXK is my conformity score for the test example X for the class K. For simplicity, I just assume that these are directly the model output, so my logits or my softmax, and I'll threshold these at tau. And so here I noticed a couple of minutes ago that I have a mistake. So this should, of course, be tau. But then at the calibration set, I assume that I have this set of exchangeable calibration examples, xi and yi. And then I compute this kind of modified alpha quantile here in order to set the threshold, right? So on the calibration set, I have 1 minus alpha coverage by construction. And then the theory basically tells us that this generalizes. So now this, I think, is very basic. And then there is, of course, an alternative view on conformal prediction, which I also very much like, and it will be useful later for the Monte Carlo conformal prediction part, is a hypothesis testing view. So instead of calibrating the threshold, what we can also do is we can test the hypothesis HK, which basically says that the true label of the example X is K. And we can do this by computing these very nice conformal p-values by simply comparing the test conformity score that I have to all my calibration conformity scores and normalizing appropriately. And can be shown that this is uniformly distributed on 0, 1, which means this is a valid p-value. So if I assume that the hypothesis HK is true, then the p-value is uniformly distributed, which means that lower thresholding it by alpha will guarantee us the coverage 1 minus alpha. And these are, of course, both equivalent, and we'll jump back and forth a bit throughout the talk. Okay, this is also nothing new. This is just an illustration on Cypher 10 that I usually use in my talks to show how it works. So we have this very simple conformal predictor on the left, and we see that the lower the alpha, the higher my confidence set size on average. Okay, so again, please interrupt me if anything's unclear, but I'll assume that people are fairly familiar. So let's just dive right into the main part, where I'll start basically revisiting the ground truth that we are used to just downloading with a data set from the internet. So how do we obtain usually the labels that we use for calibration? And of course, if we read papers, not only on conformal prediction, but also on machine learning in general, then in the methods section, the first paragraph or something, we usually have this statement that we assume our calibration examples or training examples or whatever to be IID or exchangeably sampled from this true distribution over labels and examples. In practice, of course, there's some nuance to it, because if I just look at this image from Cypher 10 here, then nobody here in this Zoom call knows the true label, right? Because I didn't take the image, I didn't downscale the image, I didn't upload the image to the web, right? And this assumes that if I were to take the image, I can actually correctly kind of classify what animal this is, right? Which is, of course, an easy task. If we now consider medical tasks, then I, as a doctor, might, even if I see the full resolution image, I might not be able to make a perfect classification. So what we usually do in these settings is that somebody scrapes the data and then we get it annotated, right? So if I look at the image, I might say it's a bird. For me, it looks a bit like a bird. People might disagree, right? But this is how we construct most of these benchmark data sets, right? And people actually did this relabeling on Cypher 10. So if you read the original paper, Cypher 10 was actually labeled by the authors. So there was like probably Alex or somebody else sitting there and annotating these images. But there was a separate paper a couple of years ago that basically re-annotated the test set using 50 annotations each. And you can see on this example here that there are quite a few people that agree with me. Quite a few people think it's a bird. There are more people, unfortunately, that think it's a cat. 23 people out of the 50 think it's a cat. And then there are a couple that are unsure between dog, frog, and deer. Okay. And then what we very often do in these cases is that we do some sort of aggregation. For example, in classification, we just do majority voting, right? So here the majority voted label might be cat, which means that not for Cypher 10, but for many data sets, you download the data set, you of course skip this annotation part. You download probably some sort of majority voted or average or aggregated labels. And in this case, using cat as a label, of course, ignores all of these raters, all of these annotators that think that it's a bird, including me. So why is that a problem in the context of not only machine learning, but specifically conformal prediction? Well, the problem is we have this assumption that we would like to have our calibration examples sampled from this distribution, but this is not entirely true, right? Because we have examples X sampled from this distribution, but our labels actually come from this annotation process and then from this majority voting, right? And just to introduce some notation, I'll basically capture this in this distribution p-vote, which I'll call the voting distribution, right? So what we have in practice, we have examples X that come from the true distribution, but then our labels very often come from this voting distribution. And the realization now is that on ambiguous examples, like this one on cipher 10, this voting distribution is, of course, not or is unlikely to be the true distribution. And an easy check for this is that the voting distribution is always one hot, right? It has like basically no entropy. Whereas the true distribution, if we believe the annotators, might actually have higher entropy, right? If we think that these annotators, the frequencies of the annotations, represent the true distribution to some extent, then we have entropy. So in this case, the voting distribution is not the true distribution to some extent. The problem is, of course, if we want to have a coverage guarantee with respect to the true distribution, but we only have calibration labels coming from this voting distribution, then we have a problem, right? Because the coverage guarantee, we don't get any coverage guarantee with respect to the true distribution. All the guarantees we get are with respect to the labels we calibrate on, and these come from the voting distribution. And so we have a discrepancy here that we somehow need to address. And just to drive this example home a bit, on a very, very easy toy example, just to visualize it a bit, I consider this two-dimensional toy example here that we also have in the paper quite prominently. And these are the true labels. So it's a toy example, so I can actually show the true labels here. We have quite some overlap between the blue and the red class, and then the green class is a bit separate. Of course, in reality, this problem is mainly due to limited observational information, right? So there might be this third dimension, which I try to kind of indicate here using my basic Google slide skills, along this unobserved third dimension. And with this third dimension, these classes might be perfectly separable, perfectly linear separable. The problem is, of course, in practice, we might not observe that, right? So you can think about this third dimension of being the high resolution image for cipher, or a full patient history in a radiology case, right? But in practice, what we see is only the radiology image, or we only see the downscaled image. Of course, we never observe these true labels. We can also have a look at the true posterior distribution in this case, where you very nicely see this transition here, this ambiguity in between blue and red, where you can imagine that this bird/cat image is actually somewhere in between, whereas a lot of these very crisp and very easy examples on cipher 10, such as this airplane, are somewhere in the green region, where it's kind of very easy, not very ambiguous. Of course, in practice, we don't observe the posterior either, but it's just like for illustration. Now, if we were to observe the true posterior here, then majority voting basically just corresponds to a kind of very rough simplification of the problem, right? It's basically Bayes' decision rule on the true posterior. We see that we now have a linearly separable problem, right? So this is kind of the difference between the right two plots, is essentially the difference between having actually labels from the true distribution and having labels from this voting distribution. So just to show that a very easy toy example, which I always like to visualize in my head. So now the problem is, on cipher 10, you might argue that it's not really too relevant. We can just use higher resolution images. And then a toy example is not relevant in practice anyway. So why are we talking about this? So let me show you kind of a real world, and actually quite serious real world case from dermatology. So here the task is skin condition classification. We are given one or more of these images. These are not like medical images in the sense that these are professional images. These are basically you and me taking images of like a skin rash with like our phone and kind of sending it to the AI or a doctor to give us a diagnosis, right? So I can't tell you anything about this image, but we essentially asked dermatologists to give us annotations. And the first difference you'll notice is that these dermatologists, they don't give you a single label like the annotators on cipher 10 do. They give you a differential diagnosis, right? So they give you some sort of ranked list of conditions. So the first dermatologist says, okay, I'm very, in my opinion, this is the most likely condition, and then hemangioma and melanoma are less likely. And we also have quite rich structure on top of these conditions. There are different sorts of categories. And the easiest one is that there are different risk categories for these conditions, which are highlighted in the colors here. So on this case, what people do in prior work is also just majority voting. Now, of course, majority voting in this case, because you have the rankings, is a bit more difficult. But I mean, there are smart people around that have figured it out and came up with like a deterministic way of how you can approximate majority voting on these partial rankings. And the majority voted label is hemangioma in this case. right? I underlined it here, and it seemed reasonable, right? It's included in many of the rankings, and in 3 out of the 6 rankings, it's actually included as the most likely condition, right? So it seems reasonable. The problem is, of course, we ignore a lot of the other conditions. Most notably, we ignore the melanoma annotations here. The differences between hemangioma and melanoma is that melanoma is actually a cancerous type, right? So many doctors might actually include melanoma as a kind of unlikely condition, but they include them because they want to test for it, right? They basically want to exclude it because not capturing kind of skin cancer is kind of has a serious consequence for the patient usually. So by doing all of our evaluation, training, calibration, and so on against this majority voted label, we actually exclude kind of all the other information we have. And in this particular example, we might actually ignore kind of a lot of evidence that the doctors see that this is actually cancer. Okay, so how can we deal with this in the context of conformal prediction now? And our goal is essentially to embrace this ambiguity ideally. Ideally, we want to kind of somehow calibrate directly against the annotations. This is, of course, not super straightforward because in the dermatology case, for example, we still want to have a multi-class classification problem, but our annotations are actually these partial rankings, right? So there is a discrepancy between the annotation format and our classification task. On Cypher 10, of course, that's not the case. The annotations actually give us single labels, and we also want to predict single labels, for example, or we want to predict confidence sets. So in order to bridge this potential mismatch between the annotation format and our classification task, we assume that we have this intermediate result, which I'll call the aggregated distribution, PAG here, that basically aggregates this ranking into a categorical distribution. On Cypher 10 on the left, that's easy. You can just like count frequencies of the single annotations. On the right, it's a bit more complicated, and I won't go into detail, but it's a very simple 5 lines of NumPy implementation of how you can basically aggregate these partial rankings into a categorical distribution. You also directly see that the top one is still hemangioma, but you see that melanoma is actually very close. Different aggregation strategies will, of course, result in slightly different categorical distributions. So there is some notion of model assumption here on the right to bridge this gap between having partial ranking annotations and intending to work on categorical distributions. On the left, of course, this is kind of purely data-driven. There's not really a modeling assumption here. Okay, and so why is this meaningful? Maybe it's worth taking a step back. Why is it meaningful to work with this aggregated distribution? The first realization is that because we will never be able to observe true labels or to identify the true kind of label, the best we can do in these cases is actually to be as good, to calibrate our system to be as good as the annotators, right? Of course, you might argue there are settings where this is not true. There are settings where we can actually get to the true ground truth, right? So for example, we could take this patient and we could kind of have the patients go through a lot of invasive tests and then in the end actually do a biopsy, right? And actually kind of basically all of medical tests are not like definite, but we would have like a very, very high confidence that it's maybe hemangioma or melanoma. But this is of course not scalable. And this is basically solving the problem by adding kind of a lot of additional information, which our machine learning model doesn't have anyway. Okay, so then kind of having realized this, yeah, please go ahead.
Yeah, so I'm curious about how you think on like whether calibration for uncertainty sets, these two notions of uncertainty, like having calibrated class probabilities versus having covered guarantees, which of these are like a better way to capture ambiguity in the ground truth?
So that's a good question. So I think there's 2 things here, right? If you're just talking about capturing the uncertainty in the ground truth, so for example, you just want to measure the uncertainty in the ground truth as you observe it through the annotations, then so we have separate paper on that where we take a Bayesian approach, where we basically, for example, have kind of a probabilistic model over these partial rankings, and then we can basically get creedal sets, right? So we can get distributions, we can get probability distributions over these categorical distributions, and then you can imagine the spread on top of these distributions kind of reflects what we call the annotation uncertainty, right? If you talk about predictive uncertainty, so assuming we train a model on these labels and then we want to evaluate this model, then I'm actually, I think it depends very much on the application. And in this particular setting on the right here, so we've worked on that before, there is actually quite a bit of incentive to work with confidence sets. Because in the medical domain, people are very used to having these kind of differential diagnoses. So it's very natural to predict confidence sets, and I think that's also a good match for conformal prediction then. So it depends a bit. So there's this. So I like to distinguish essentially between the ground truth uncertainty, and I'm happy also to share the separate paper we have on that, where we basically say, okay, ground truth uncertainty is also non-trivial. There is actually inherent uncertainty to that, where it's actually hard to pick a specific label because of the limited information. But then there's also other sources of uncertainty on that side that come through the labeling process, right? The annotation tool not being perfect, the annotators not being super experienced, the annotators having a bad day, and so on, tasks being misspecified, right? And kind of measuring all this uncertainty, I think, is non-trivial, and we kind of follow the Bayesian approach, but I think there are many others. But then for the predictive uncertainty part, I think it's specifically in this case, it's actually quite meaningful to think in a conformal way and aim to produce confidence sets.
Yeah, makes sense.
Does that make sense?
Yeah.
Yeah, but that's a good question, because it's I think it's valuable. Like, even if we have some sort of model assumption here, it's important to keep in mind that this is not the predictive model. This is really kind of additional modeling that we have to do on the ground truth side in order to work with these annotations that we have. Okay, so as I said before, I'll spend quite a bit of time basically talking about this problem, and this is kind of the first part now. So now comes maybe the more interesting part for people interested in the conformal prediction bit, is how can we now calibrate against these distributions, right? So we assume that we can get these aggregated distributions somehow, and the difference is basically can we go from calibrating against single labels to calibrating against distributions? Okay. And the first step here is talking about or figuring out what does coverage mean in this setting, where we evaluate or where we kind of calibrate against distributions and not labels. And this slide is a bit complex, so let me walk you through. So just the first message up here, I tend to call these aggregated distribution plausibilities, because depending on how you model it, you might actually want to call them plausibilities, because they might not be kind of normalized distributions all the time. So we assume that we have, for each example, for each calibration example xi, we have this plausibility vector, which is a categorical distribution on cipher 10 here. So you see that this reflects just the plot on the left. We have 32% voting for bird, 46% for cat, and so on. And then we have a confidence set. In this case, I'll say the confidence set includes cat and dog. And so now how do we evaluate coverage? Right, so in a majority voted case, it's easy. It's a binary event. We basically check, is the majority voted label included? Majority voted label is cat. Cat is included, so we have coverage. An alternative way that we propose and call aggregated coverage is, instead of having this binary event on top of the majority voted label, just basically see how much of the plausibility mass do we cover by our confidence set. Right, so we cover cat, that's 46%, and we cover dog, that's 16%. So our aggregated coverage for this particular example would be 62%. Right, so the first thing you notice is that we make the switch from like a binary event per example to this kind of continuous event, continuous variable between 0 and 1 for each example. And just maybe more interesting, let me actually reveal the whole thing at once. And the interesting thing is now to realize that evaluating this way should be equivalent to actually having the coverage guarantee of the true label being included, if we were to know the true label, which of course in practice we don't, right? So what we want to have is we want to have a guarantee on this, on the left here, where we say the probability, where we take the probability of the true label y that we don't observe being in the set. Of course, to make clear that we might have a modeling assumption here, I also have the distribution over the aggregated distribution. And this is just easy rewriting, right? So this is a binary event, so we can rewrite this as an expectation. Then we basically split up the expectation by realizing that the examples are actually sampled from the true distribution, but the labels are sampled from this aggregated distribution, right? And then we just kind of split this up, and then we can actually very easily see how we can kind of evaluate this in practice, because the inner expectation is just like a sum over all classes, and basically weighting the binary event of K being included by the corresponding plausibility, right? So this is exactly what we did here. We have to sum over the plausibilities, and cat and dog is included, so we basically sum these two respective numbers. So what this basically tells you, so this actually looks quite trivial, but what this actually tells us, if we were to perfectly approximate the true posterior P, right, then this notion of aggregated coverage actually coincides with the true coverage, right? Of course, in the toy setting, we observe both the true labels and the true posterior, so it's not interesting. But in practice, we only observe this aggregated distribution by aggregating the annotations, but we don't observe the true label. And in this case, it's actually important to state that how we evaluate aggregated coverage is actually the right thing to do here. Okay, another important thing to realize is, of course, that like conformal prediction is always marginal, right? Unless we do some extra work. And usually it's marginal across the test examples and, of course, overall a calibration set. But in this case, we are also marginal over the labels, right? Because for each example, our calibration procedure not only decides which examples I want to cover, but also how much of the plausibility mass for each example I want to cover, right? And this is why where these cases happen, right? So the calibration procedure might actually decide that for this particular example, I will not be able to cover all the plausibility mass, so I'm happy with like something in between. Okay. So just as a simple illustration, coming back to the toy example, if we start with the, yes, there a question? No, okay. Otherwise, please interrupt me. So just a simple example on a toy example, we start with our voted labels and we perform standard conformal prediction on these voted labels, right? So if we calibrate on voted labels, we assume that we get the target coverage against the voted labels. And this is what we evaluate in green, right? So as you might know, we usually do multiple test calibration splits. This is what the histogram is about. And then on average, we would expect that we get the target coverage of, in this case, 95%. And this is what we do. Okay, so this is so far so easy. So now what happens if we actually assume we know the true posteriors and we actually evaluate aggregated coverage? Of course, in this case, aggregated coverage coincides with the true coverage. And we do this in blue, and you can see that there's obviously a significant gap, right? So if we calibrate with the voted labels, we think we get coverage 95%, but we only get this coverage against the voted labels and potentially not against the true labels that we never observe. Right, and this gap is quite significant. And in the paper, you can also find that this gap obviously scales with the ambiguity, right? The more these three Gaussian distributions overlap, the higher the gap, versus if these Gaussians are perfectly linearly separable, then these two histograms would coincide. Okay, so the question is now, how can we essentially close this gap by kind of doing something smarter than calibrating against the majority voted labels? And this is where Monte Carlo conformal prediction comes into play. And you'll also very easily see why we call it Monte Carlo conformal prediction. So what we do is we assume that we have these plausibilities. And we just say we repeat each calibration example m times. Okay? And then we construct in an augmented calibration set. And the augmented calibration set looks as follows. For each repetition of the example xi, I randomly sample a new label from the corresponding plausibilities. Right? So if I go back to my example here, I would repeat this example maybe 10 times. And for each repetition, I would sample a label, right? So on average, I would expect that maybe roughly 3 or 4 of these are bird, 4 or 5 of these are cat, and so on and so forth. Okay, so this is what I do. The problem with this is very apparent that if we repeat these examples more than 1 times, which we might want to do, and I'll talk about it in a bit, then we don't have exchangeability anymore, right? And a very easy way to see this is by writing the joint distribution over our test example Z here and all of our calibration examples. And now you'll notice that the first calibration examples are, of course, repeated instances, right? So now if I take a random permutation, the likelihood that I'll preserve this structure of repetitions is very low. So very likely the joint distribution will just be 0. So we are not invariant to permutations, so we don't have exchangeability. And then we lose the coverage guarantee of conformal prediction. And there's actually a very simple fix for this. And this is just adjusting the quantile computation. So if we perform split conformal prediction on this augmented set, we just need to update the quantile computation from from this alpha times n plus 1 over n to this slightly more complicated notion. Of course, in the limit for large n, this will still roughly be an alpha quantile, right? But for the theory, it's actually important that we now have these additional terms depending on m. And you will also directly see if m is equal to 1, we just have the original quantile. Okay. And it is possible to derive these thresholds directly, but I think it's not very easy to follow. So what I'll actually do, I'll show how we got there roughly on the p-value side, right? So we basically look at the equivalent formulation using p-values, and this looks as follows. The p-values are, of course, just like summing over all calibration examples and comparing our conformity scores to the conformity scores on a calibration set. But because we now have m times n calibration examples, we can just rewrite it as kind of a sum over both n and m, and then in the denominator, we also have this additional factor of m. So now, for a second, let's assume these plus ones here, because these are always a bit annoying. And then it's easy to realize that we can rewrite this as an average of p-values, right? So for each sample m, right, each sample m means that a specific sample is basically includes specifically sampled labels for each example according to the possibilities. And we just average these different samples for each class k. Now, the problem is, of course, that these individual p-values we get here are not valid p-values in the conformal sense, because in order for this to be true, we would have to have these corrective terms here in order for the p-value to be uniformly distributed on 0, 1, and actually give us valid guarantees, right? And then we just work our way back. We basically say, okay, in order to have these additional terms here, what do we need to change? And the main thing to change is essentially that we just change the denominator a bit, right? So if we change the denominator here, then we can see this as a problem of averaging p-values. And averaging p-values is a very well understood problem. And there is a lot of work that basically shows that if we average these p-values, we get a coverage guarantee, but we lose a bit of coverage. So instead of 1 minus alpha, we get 1 minus 2 alpha. Okay. So yeah, so in summary, Monte Carlo conformal prediction can be formulated as this averaging of m p-values problems. We have a coverage guarantee of 1 minus 2 alpha. This might actually look familiar to many because we have the same problem in, for example, cross-validation based conformal prediction and cross-conformal prediction and so on, where we also kind of have this 1 minus 2 alpha. And you can make a very similar argument in cross-conformal prediction that this also stems from averaging p-values. In our case, we can improve over this. We can get arbitrarily close to 1 minus alpha if we have an additional calibration split. So if we have enough data and we are willing to split the calibration set in half, then we can get arbitrarily close. Of course, as you might know, the main problem with small calibration sets is that then the variation in our coverage, depending on the calibration set, might be very high. So if we don't have enough calibration examples, this might not be what we want to do. And also, as in cross-conformal prediction and jackknife conformal prediction and so on, empirically, we actually never observe the 1 minus 2 alpha. Empirically, we always get 1 minus alpha on average. And I really try to find out or find examples where we can at least see a slight drop by basically, for example, sampling these labels here in a particularly bad way. But it's really difficult. So I'm actually fairly confident that empirically we'll always get 1 minus alpha on practical examples. Also important to note that if we don't have any ambiguity in the problem, meaning all our plausibilities are always one hot, have 0 entropy, meaning all our annotators always agree, in this case, we actually recover standard conformal prediction, right, for any m. Of course, if we don't have any ambiguity, we might not want to use a larger m than 1 anyway. Another nice thing is that this is actually a per example argument, right? So this Monte Carlo conformal prediction works on a per example basis, meaning on the ambiguous examples, we improve coverage, usually by sacrificing a bit of efficiency. On the unambiguous examples, the performance is usually very similar to standard conformal prediction. And this is important in practice because most of the data sets we work with are neither totally ambiguous or totally crisp, right? There is, of course, a spectrum. Some examples are difficult and some are not. Okay, so let me show you some concrete examples on the dermatology data we have. So here is basically standard conformal prediction against the majority voted label, right? So in this example I showed earlier here, this is basically doing the calibration against hemangioma, and we do kind of the same majority voting on all examples. Sorry for skipping back and forth. And then in blue, we also evaluate against the voted label. So we have voted coverage. You can see that we calibrated for 72%, and we also get on average 72%. Of course, we have a smaller calibration set, so there is quite a bit of spread here. But if we now evaluate aggregated coverage against the plausibilities, then you can actually see quite a bit of a coverage gap. So this is kind of nearly 10%, which means that we think the model gets 72% coverage, but in practice, against the true label as represented using this aggregated distribution, we're actually only getting 62. And on the inefficiency side, we need on average like 2.6 conditions in our set to get this. Now, if we go to Monte Carlo conformal prediction, the main thing that changes, of course, the histograms look a bit different because randomness, but the main thing that changes is that both of these histograms move to the right, right? So now we get a target coverage of 72 point something percent using aggregated coverage, and then the voted coverage is, of course, just shifted to the right. It's now at 82 point something percent on average. Okay, and the cost we pay for this is higher inefficiency, right? So on average, the number we need, the number of classes we need to include goes from 2.6 to 4.5. Right? You can, of course, now do an analysis per example, and you will see that on very easy examples where all the annotators agree, usually the inefficiency increase is very small, and on those examples where we have a lot of ambiguity, it's very large. So here are two ambiguous examples. The first one is the one that I showed before. So here I show the plausibilities, and in green I basically mark which classes are included in the confidence set. You can see here that we get a aggregated coverage of 41%. So 41% of these plausibilities are covered. And then using Monte Carlo conformal prediction, we just include more classes, and we get on average to 79%. Right? And the important thing, of course, that's why I like the example, is that we suddenly also cover this cancerous melanoma type here. Right, which is important, and because it's quite present in a lot of the annotations, it has quite high plausibility, so we would expect the method to cover it. On the bottom is kind of a very difficult examples where all the annotators disagree, so we have equal plausibility for all of these classes. And of course, Monte Carlo conformal prediction won't do any magic there. Of course, we can improve if we calibrate for higher coverage, but here too we basically include a bit more of the plausibilities. Okay, so in conclusion, Monte Carlo conformal prediction is nothing else than doing conformal prediction with sampled labels, where the labels are sampled either directly from the annotators, which we can do on Cypher 10, or from these plausibilities that are somehow aggregated from the annotations we have. And the first few bullet points are really to reiterate this point that on ambiguous examples, there's actually a difference between kind of having this majority voted label or having simple deterministic aggregation and working with the plausibilities. And then the Monte Carlo conformal prediction bit is just how can we use this information to calibrate better. And yeah, this is it. So we establish the coverage guarantee 1 minus alpha or 1 minus 2 alpha, depending on the setting. And I just want to note that this actually directly applies to multi-label classification too. Right, so this also establishes a nice coverage guarantee for multi-label classification, where people also use to repeat examples. And we also have a use case for robustness or data augmentation in the paper if people are interested in that. Okay, so I'll stop here, but happy to take any questions.
Thanks a lot, David. While others think of questions, is there a trade-off between robustness when you calibrate just with respect to p-vote versus p-aggregate? Is there an efficiency robustness trade-off? Because if you just calibrate with respect to p-vote and the distribution of annotations is varying from one environment to the other, would you get better coverage in external data sets at the expense of efficiency, or is there like a hidden assumption about the exchangeability of annotation distributions that you're assuming here?
Okay, with robustness, you mean kind of generalization to like a new data set, or?
Like, yeah, if the distribution of the annotations are changing, because like these are just
okay.
Like, so if you calibrate with respect to p-vote, that's probably more robust than calibrating on p-aggregate, but maybe that's not true.
Yeah, that's actually a good point. That's a good point. So let's assume that, for example, we change the annotation tool, or we change the rater pool, right? Then we would see a shift in the raw annotations, but the shift might actually be less pronounced and not be there in the majority voted label. And then I assume you would be more robust. But I think it's a hard argument to make, because so especially in this example that I always like to show here, right? You can imagine, so these two conditions seem to be so equally likely that if I change the labeling tool, like whenever I change the labeling tool a bit, the top one label might actually change quite a lot, right? So I think so. The majority voted label might be more stable with respect to different annotation processes, on average across the data set, assuming that we have a lot of crisp examples in the data set. But for the examples we actually care about, we might actually see that the majority voted label is also not very robust. And the problem with the majority voted labels in these cases is that it's a binary thing, right? The majority voted label switches or not. So in one case, so you always ignore, if you have two classes and a completely uniform distribution, this is the worst case, right? You always ignore 50% of your evidence, right? So yeah, on average, I think it will be more robust with the majority vote labels. In these ambiguous examples, which you might care more or less about, depending on your task, it might, however, kind of backfire a bit. And in the separate paper that I mentioned on, we look at kind of how do we evaluate AI models in these cases, where we basically model the annotation process and then we sample different annotations. And then you see exactly this behavior, right? You see like a model that predicts hemangioma as a top one class. But then, and then if you evaluate against the majority voted, it looks perfect. But if you add a bit of noise on top, you only cover it in expectation 50% of the, or you only have the right prediction in 50% of the cases, right? So it's I think it's an interesting question, this kind of robustness argument. But given that we really motivated from these really ambiguous cases, I think in these cases it won't help too much. It's an argument, right? On this data set, roughly 50% of all the cases are fairly ambiguous, right? So here you might actually care. On Cypher 10, for example, the example I showed before was super cherry-picked, right? There's like maybe 0.1 or even less % of the examples where you actually have disagreement, right? And then on Cypher 10, you might simply not care.
Yeah, I see. Other questions?
Questions, or also happy to take comments or recommendations on related work or something. People have any thoughts?
So one thing I was thinking about is like connection with weak supervised, with the weak supervised learning literature. Like if you think of these annotators are not being dictated, but you're actively using multiple weak supervision sources, is there like a way to optimize the annotators, or like what would be the criteria for like deciding where the annotations should come from if you're doing this automatically and
Yeah.
like
Yeah, that's a good question. So maybe one comment to that. So one interesting connection is definitely so not this active data collection part, but also like weak supervision in general. So there's quite a bit of work on, for example, partial label learning, which is like fairly similar. So I just wanted to point that out. In terms of active data collection, that's an interesting thought. And to be honest, we haven't really connected this work to that. So one thing I think that it depends very strongly on is how you actually model the annotation process, right? So on Cypher 10, for example, it might be fairly easy to basically take knowledge from maybe the produced confidence sets and kind of route that back into like which examples do we want to annotate, like which examples do we want to get more annotations on. In these examples on the right, it's a bit more difficult because we have this intermediate step that goes from the raw annotations in terms of partial rankings to the categorical distribution, and you would have basically to think your way through it. So on an example level, you can probably do it somehow by basically saying, where I observe, for example, a larger increase in inefficiency from like majority voted calibration to Monte Carlo conformal calibration, I usually have more ambiguous cases. But there is a problem with that, which is that like standard conformal prediction is usually assumed to not care about the type of uncertainty, right? Conformal prediction doesn't distinguish between epistemic and aleatoric uncertainty, for example. And this is the same here, only that with Monte Carlo conformal prediction, we have another source of uncertainty, which is kind of this ground truth uncertainty, which means that you can't actually disentangle between the predictive uncertainty and the ground truth uncertainty. And if you are sure that it's ground truth uncertainty, it's actually very difficult to decide, is this inherent uncertainty due to limited observational information, or is it just some labeling noise, some inexperienced annotators that I can improve on? Because in this active data collection, ideally, of course, you want to identify examples that have high uncertainty, but not high inherent uncertainty. So you can reduce the annotation uncertainty essentially, right? So you can say, okay, like on this example, if I use different annotators, or if I improve the labeling tool, I'm sure that I can reduce the uncertainty. But on this example, for example, so we discussed this with dermatologists, and it very much looks like that this is an example that's just difficult using limited information. And then you can ask like 10 more dermatologists, but you might not kind of get more information.
So on a related, on a related note, is the Monte Carlo procedure going to inflate the sets for instances where you have like very strong consensus with the majority labeling, or are you sampling from the histogram of each specific instance?
Yeah, I'm sampling from the histogram of each specific instance. So what you would usually see, so of course there is a general increase in inefficiency, which you can easily see by assuming that the threshold that you calibrate will usually be a bit lower across the board, right? Yeah. But in general, the effect you will see is usually that the increase in inefficiency is largest for examples where you have a lot of disagreement and a lot of ambiguity, right? You of course don't know whether this disagreement stems from inherent uncertainty, like aleatoric uncertainty essentially, or from like annotation noise or annotation uncertainty, or however you call it. But you'll see the largest increase for these. And that's why I like to kind of highlight this point earlier here, that Monte Carlo conformal prediction is basically, it reduces to standard conformal prediction on ambiguous examples. Right, so if you have only unambiguous examples, if you have only crisp examples, it's standard conformal prediction. If you have a mix of these, then the distribution, the mix basically depends on like kind of says how much of an inefficiency increase you have, right? If you have data sets that is very ambiguous, like most of the examples are ambiguous, then it will be across the board. But if it's like cipher 10, you only have a small fraction of disagreement examples, then you will probably only see like an inefficiency increase on those, and then the remaining examples will stay fairly similar. But also, this of course also depends on training, right? So if you train your model, let's say cipher 10, where you only have like 0.1% of the examples with disagreement, but your model is so overconfident that it always includes it always gives you a probability of 1 for one specific class. Even if this class is wrong, you can see by an easy argument that if only like 0.1% of my examples are ambiguous, then my threshold or my p-values will only change by like a very small amount, right?
I see.
Yeah. I hope that made sense,
Yeah.
but otherwise follow up.
Any other questions?
I just had a...
Go ahead.
You see me? Okay. I just had a comment and more of like a question. Like thank you.
Yep.
This is great. So you mentioned about like how we're like through the Monte Carlo procedure, we're able to like include diagnosis like melanoma, which are like maybe less plausible, but then like there's still like high risk. So I had like a couple of like just like broad questions or maybe ideas, like are there ways to like moving like from prediction sets here to like mode of decision making? Because what we ideally want to do is like if this is a differential diagnosis, then we want to move in the order of like trying something out, and then like that is not coming, and then basically like finally we want to see like is like melanoma that we don't want to try it out like the first step. So is there a way to like extend the procedure or have like you like use it for like decision making where we can like sequentially make these decisions? Because I feel like the partial ranking is great and might it like in some way implicitly captures that?
Yeah. So there's quite a bit to unpack there, I think. So the first thing is, of course, that because the annotations are these partial rankings, ideally, of like the easiest way is to also predict like uncertainty estimates on partial rankings. Of course, having confidence sets on top of rankings is kind of a bit annoying because you kind of explode your sets, right? It's a bit like multi-level classification. So this is a bit tricky. And we didn't try it, so you were very welcome to try it, and I'm curious how well it works. But I would expect that you usually get like very large sets, and then because these are all partial rankings, might be a bit difficult to kind of use that as a prediction and kind of communicate it properly or something. The other thing on decision making, this is actually a very interesting point. I don't have any thoughts on how to do it in a sequential manner. Also, I'm not sure if there are any data sets out there where you could very easily try this, because in the sequential thing, you would probably do something like you want to predict a very conservative confidence set that really takes like all the ambiguity into account. And then you basically perform like an additional test or something. You get more information and then you repeat it to some extent. I'm not sure if there are data sets like that. But what I want to mention is that we haven't tried it, but I'm fairly confident that you can. Oh, sorry, I think you're seeing like half of the chat all the time. That you will be able to do something similar on using conformal risk, for example, right? Where you don't do Monte Carlo conformal prediction to have like a coverage guarantee, but basically to guarantee some risk. And then you might be a bit more flexible in terms of turning this into like a decision-making system, right? Instead of like calibrating for coverage, you could also calibrate the risk that cares about abstention or deferral to a doctor or something like that. Even though I'm fairly confident that it should work, I actually like it would probably need some work to write it down. The immediate problem in my head right now is that I think nobody really written down if you can get p-values for kind of conformal risk-like things. I think it should be. If you can, then you can apply the same argument that I just outlined, essentially. Yeah, maybe that's an interesting direction. So I'm maybe that's not sure if that answers all your questions, but I think it's an interesting direction, and I think the conformal risk thing could be an intermediate step where you go from like confidence sets to more like an action of like abstaining or deferring or whatever risk you are interested in.
Okay, so thanks so much, David. In the interest of time, I think we can move to the next talk. So
Yep.
if you have any other questions, I think you can email you.
Yeah, sure. I mean, feel free to follow up and shoot me an email if people are interested in it. And yeah, thanks again for having me.
Thank you so
very
much.
Appreciate the invitation. And then I'll also drop off because it's quite late in London.
Okay.
But I hope you enjoy the next talk.
Thank you.
Thanks. Bye.
Bye.